We're continuing our exploration of 7.4, partial fraction decomposition. Here we're going to cover case 2, repeated linear factors. So our objective remains the same, to integrate rational functions, but here the denominator is going to be a product of repeated linear factors. And so I'll show you what that means. We're going to suppose that q of x has a specific form. I'm going to use product notation again. So uppercase pi means we're iterating a product. So I is our dummy variable, which just means the subscript is going to tell us which term we're on, or which factor we are on in the product. And just like before, the terms themselves should look very similar. They should be linear themselves, but raised to some power, r sub I. So each one has a power corresponding to it. So what that would look like is, for each of these factors, it has a corresponding power possibly greater than 1. And so then there exist a sub 1, a sub 2, a sub r sub 1, b sub 1, b sub 2, b sub r sub 2, and so on, until we exhaust the full. So each linear factor that is distinct from each other gets this set of undetermined coefficients. M sub 1, M sub 2, M sub r sub k. So that would be the last set of them. Such that this fraction, which is the rational function, can be written as a1x plus b1 is the first denominator with a sub 1 in the numerator, plus then the next one is going to be raised to the second power, so it's going to be squared, but it's the same linear factor inside. Whoops, and it's very messy. I'm going to try to be neater with my writing. Plus and then the last one, the denominator is going to be the very last, or the highest power on the same term. So the r sub 1, a sub r sub 1. And we repeat this for every distinct linear factor that appears here. Boy, I'm getting kind of messy, aren't I? So a sub m, x plus b sub m is the denominator there. M sub 1 plus and then all the way up to a sub m x plus b sub m raised to the r sub k. I guess we should have gone up to k. It doesn't matter, but m sub r sub k. Okay. What does this look like in practicality? So let's think about something like q of x equals x minus 1 squared times 2x plus 7 to the 5th power. So that means that we're going to focus on these powers, right? So these powers really are what we call the multiplicities of the roots. So each of these sets of parentheses gives us a distinct linear factor, and the power is what tells us how many of the iterations we need to produce. So that means that our corresponding p of x over q of x is going to have the form a sub 1 over x minus 1 plus a sub 2 over x minus 1 squared plus b sub 1 over 2x plus 7 plus b sub 2 over 2x plus 7 squared, and so on until the last one is going to be b sub 5 over 2x plus 7 to the 5th power. Okay, does that make sense? So each linear factor is going to be repeated in this sum, right? The sequence of terms here, up to the amount of times equal to the power. Okay, let's see one of these in practice. It's easier to see it with a real example. So our example here. This is a standard example, okay? So we're going to have, in this case, two distinct linear factors, one repeated twice. And keep in mind that we're going to be able to combine the cases that we have depending on what factors we have in the denominator. So it's not always going to be pure, you know, we only have one that's repeated twice and so on. So we're going to find or evaluate the integral of x plus 1 squared, x plus 2 in the denominator, all under x squared plus x plus 1 dx. Okay. So when we do this, let's first figure out what the decomposition should be, right? So we're going to seek, basically you want to add up the powers, and that'll tell you how many variables we're going to be looking for. So one has a power of 2, the other one has a power of 1. That means we're actually looking for 3 variables here. So we seek capital A, capital B, capital C, such that, these are real numbers by the way, right? X squared plus x plus 1 all over x plus 1 squared times x plus 2 is equal to a over x plus 1 plus b over x plus 1 squared plus c over x plus 2. Okay. So, once again, we're at the point where really we're just going to reduce this to a linear system of equations. We have 3 unknowns, which means we better have 3 equations, which we'll get. We will get 3 equations. Okay, so let's just go ahead and multiply it through by the LCD. We get x squared plus x plus 1. Remember that the LCD is just going to be this thing right here. So that means when you multiply a by that, or the first term by that, there's going to be a cancellation of just one x plus 1. So you get a times x plus 1 times x plus 2 plus b. This one, both x plus 1s get canceled. You just get x plus 2. And this one, you get cancellation of an x plus 2, and that leaves the x plus 1 squared. Okay. And now what we can do is we can just go ahead and multiply it all out, and hopefully we get something nice and simple. So a times x squared plus 3x plus 2 plus, sorry, that's my dog. And that's the other one. They're both yappers. X squared plus 2x plus 1. And they're fine. They just, the neighbor's dog must be out. And they're like yelling at each other? I don't know. I don't really understand dogs. I'm more of a cat person now. Anyway, all right, so let's see. we do have some x squared terms on the right side, some x terms on the right side, and some constant terms. So let's just go ahead and combine those. So we get a plus c x squared plus what looks like 3a plus b plus 2cx plus 2a plus 2b plus 2c. Okay, the reason why I'm writing it like that is to exploit, basically I want to make clear what's happening here when we say we can split this into 3 equations. And it's a fact of polynomial algebra. Basically, it's this. Every polynomial can be uniquely expressed as the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 1x plus a 0, okay? We know this. This is how we usually represent polynomials. And because of this, if we have some other expression for it on the other side, so let's call it b sub n x to the n plus dot 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 plus b sub 1x plus p0, okay, or b naught. If we have 2 different expressions for this polynomial in this way, the only way that this is possible is if b sub n is actually a sub n, b sub n minus 1 is actually a sub n minus 1, b sub 1 is actually a sub 1, and b sub naught is actually a sub naught. All of that is to say the coefficients must actually be equal to each other. Okay, so that's why we get one equation per power of x. So when must be equal to a plus c. 1 must be equal to 3a plus b plus 2c. 1 must be equal to 2a plus 2b plus 2c. Okay. All right. So, good so far. Not too bad. Like I said, there are a couple of different ways that we can actually, work through this, through solving this linear system. I'm going to introduce a way that is more commonly covered in Math 410, which is Introduction to Linear Algebra. That said, you are perfectly equipped to learn it now. I'm not going to hold you responsible for learning it, but I just want to show you this technique, which is called Gaussian elimination, because in fact we can solve any linear system at all using this technique. Okay, so the first thing we're going to do is actually I'm going to write out this system where I'm going to order it basically the opposite way. So I'm going to put the variables on the left side. So a plus c, I'm leaving a gap there on purpose, equals 1. 3a plus b plus 2c equals 1. And then 2a plus 2b plus 2c equals 1. Okay, I've lined up basically the variables in each equation. So I have 1a plus 0b plus 1c equals 1. 3a plus 1b plus 2c equals 1. And then the last one has all the coefficients in front. So here's the point. We're going to represent this in matrix form. Okay, so matrix, and actually we call this the augmented matrix form. The names aren't terribly important at this point. Okay, so like I said, we're not holding you responsible for learning this, but this is the idea. So I'm going to represent this as the augmented matrix of the coefficients, where the first row is going to be the first row coefficients. And importantly, I'm going to put this vertical bar to separate the coefficients in front of the variables from the basically the constants on the right side. Okay, same thing for the second row. at this level, all you need to know about this technique is that we're essentially whooshing away unnecessary details and using the same techniques that we use in elimination and in the elimination method that we learned in Math 120, and generalizing it to get more powerful tools that don't actually change the value of the system. Okay, so it's going to be equivalent to the same thing that we started with. Just this is an augmented matrix form, where implicitly what we're saying is we're taking some matrix of coefficients, multiplying it by the column vector of variables and setting that equal to the column vector of constants on the right side. Again, all words that you don't necessarily need to know at this point. All we're saying is these are equivalent. Okay, we can go back and forth between these two. Okay, so the point is this: what we want to reduce the matrix to something that looks like this. Okay, we want a 1 to be the leading coefficient in that first row, followed by 0 and a 0, and then some number over here. Okay, I'm going to call it C1. The second row, I'm going to make it look like 0, 1, 0, and then the second row, and then a C2. The last one is going to look like 0, 0, 1, C3, and then that closes it off. Okay. The reason why I know that it's going to look like this is because we're guaranteed to have a solution here, a unique solution, in fact. So, again, these are all details that you don't need to know right now. If you're curious, we can talk about it. But we want it to look like that, and we're going to apply a few operations to this augmented matrix to make it look like that. Okay. So the key insight here is that we're going to need to get rid of a few pesky numbers. So notably, we're going to get rid of this, this, change that to a 1, get rid of this, okay? And we'll do that using what we call the elementary row operations, okay? So, but we'll go slowly. By the way, I just wanted to let you know, so because you're not being held responsible for this, you are free to skip through this part if you're not interested in seeing this technique. Just use whatever technique you want to use to solve this linear system. Make sure that it's a technique that you can use over and over again, right? Okay. So let's go ahead and reproduce so our intermediate task is to reduce that matrix, augmented matrix. So 1, 0, 1, 1, 3, 1, 2, 1. And last one I think is all 2s and then a 1. There we go. Okay, so first order of business is to get rid of the 3 and the 2 in that first column. Okay, so what we can do here is we're going to apply one operation at a time. Okay, so I want to change that 3 into a 0. How can I do that? I'm going to work with my row 1. My row 1 is going to be like the kernel of the action. So what I'm going to do is I'm going to take row 2. So this R2 represents row 2. And I'm going to replace it with row 2 plus -3 times row 1. Okay, what does that mean? So every number or element in row 1, I'm going to multiply by -3 and add it to row 2. So what does that row look like? Let's go ahead and actually write that out. That row looks like 1 times -3 is what is it? Oh yeah, sorry, I got distracted. -3 plus 3 is 0. Then 0 times -3 is still 0. Plus 1 is 1. Same thing with 1 here. Times -3 gives us negative 3, plus 2 gives us negative 1, augmented with 1, so we have to do the right side too. 1 times negative 3 is negative 3, plus 1 is negative 2. Okay, so we're going to replace the entire second row with that line now. Okay, so step 2 is to replace row 2 now with this new row that we just constructed. And this is a totally valid operation. Okay, this is why we're using this. And notice that row 1 is actually not going to change, because we just took a copy of it and we added it to row 2. And that doesn't change fundamentally the structure of it. It doesn't change the system. It's an equivalent form. We could always go back and undo it. Okay, next step. Let's get rid of row 3's number 2, the first one. So row 3, I'm going to replace it with row 3 plus negative 2 times row 1. I'm still going to use row 1 because it has that 1 in the same column. So that'll allow us to change that. So what does that row look like? So negative 2 times 1 is negative 2 plus 2 is 0. That's what we wanted, right? Otherwise we wouldn't have done anything. 0 times negative 2 is 0, plus 2 is 2. Negative 2 times 1 is, negative 2 times 1 is negative 2, times 2 is 0, okay. And then, lastly, negative 2 times 1 is negative 2, plus 1 is negative 1. Okay, so then that now means we have this system. Whoops, hang on. This is our system now, okay? 1, 0, 1, 0, 1, negative 1, 0, 2, 0, and then make sure you line up and keep the corresponding last column. So negative 1 is now going in the bottom row here at the very end, okay? This is what it looks like so far, okay? Okay, what can we do now? Okay, so at this point, what I'm going to do, because notice that there's a 0 here so there's a 0 right here. We don't actually want that. We want there to be some number that's not 0 there. So what I'm actually going to do is I'm actually going to switch row 2 and row 3. So row 2 is going to switch with row 3. I'm going to represent it like that. All that's saying is we're just going to switch the order. That doesn't change the system, okay? So that looks like 1, 0, 1, 1, 0, 2, 0, negative 1, 0, 1, negative 1, negative 2. Okay, fundamentally the same, okay? We haven't really changed anything. But this is important because now what we're going to do is we're going to use that row 2 to eliminate this 1 right here, okay? So how do we do that? Whoops, here we go. By the way, so this is the original, right? Here's step 1, here's step 2, here's step 3. All right, so now what we're going to do is we're going to multiply row 2 by something and add it to row 3. So row 3 is going to be replaced by row 3 plus, and then how do you cancel that 1 with a 2? You can multiply by negative 1/2 times row 2, okay? What is that going to leave us with? So when you have two zeros right above each other, that means nothing's going to change. There's just going to be 0, okay? Now that we have zeros, the zeros don't change. The 2, when we multiply that by negative 1/2, we get negative 1. Add that to 1, you get 0. And then the 0 again, that doesn't change anything. So the last one here is going to be negative 1. Then negative 2, multiply that by negative 1. Sorry. Then negative 1, multiply that by negative 1/2. It gives you 1/2. Add that to negative 2, and you get negative 3/2. Right? Follow me so far? Doing good? Okay. Then, our new system, again, this is all equivalent, should look like this. Okay, we're getting close. The only last few things that we need to do is we need to get rid of this 1 and change this to a 1 and this to a 1. And then that will give us the full solution. Okay, and I'll show you why that works. So, first things first. Now that we're on to step 4, what do we need to change? We'll take it one at a time. What we're going to do is we're going to take row 1, and we're going to replace it with row 1 plus row 3. Why would that work? If you just take what's in row 3, this negative 1 here, is going to, if you add that to 1, it cancels it out immediately. So that works. So what does row 1 end up looking like? Let's go ahead and replace that. That ends up looking like 1 plus 0 is 1, 0 plus 0 is 0, 1 plus negative 1 is 0, augmented with 1 plus negative 3/2 is negative 1/2. Our first row is now 1, 0, 0, negative 1/2, 0, 2, 0, negative 1, 0, 0, negative 1, negative 3/2. Okay, almost there. Here I'm going to do 2 steps in one. Okay, I'm going to go ahead and replace row 2 with, I'm just going to divide it by 2. So 1/2 times row 2. That's valid. We're just taking the entire equation and dividing it by 2, essentially. Row 3, I'm just going to change the sign on everything. So negative row 3. What does that look like? Let's go ahead and do that. Those 2 steps together. So the first one, row 2, dividing it by 2, is going to give us 0, 1, 0, negative 1/2. And then row 3 is going to give us just changing the signs on everything. So 0, 0, 1, 3/2. All together then, that means our final form is 1, 0, 0, 0, 1, 0, 0, 0, 1. We have negative 1/2, negative 1/2, positive 3/2. Okay, and I claim that this is what we wanted. We're done. Why? I'm going to convert this now back from augmented matrix form to now the original equation form, which is, if it became this augmented matrix, 1/2, negative 1/2, 3/2. Was that right? Let me double check. Sorry, both the first and the second row were negative in that last column. So equivalently, back in equation form, remember that the numbers to the left of that solid black line are the coefficients for the A, B, and C. So that first equation row becomes 1A plus 0B plus 0C equals negative 1/2. The second row becomes 0A plus 1B plus 0C equals negative 1/2. The third row becomes 0A plus 0B plus 1C equals 3/2. Okay, here's why this gives us exactly what we wanted. Simplify what these coefficients mean, right? The first row, anything multiplied by 0 is 0. So you just get A equals negative 1/2. The second row, everything cancels but B. B equals negative 1/2. The third row, everything cancels but C. C equals 3/2. That's it. We solved it, right? That was our original intent, solving this system. So this was an example of Gaussian elimination. This is a skill that you typically learn in Math 410, which is linear algebra. All of that said, we now have shown, so all of that is now to say that our integral becomes, if it was originally the integral of x squared plus x plus 1 all over x plus 1 squared x plus 2 dx, that is now going to be the integral of -1/2 over x plus 1 plus -1/2 over x plus 1 squared plus 3/2 over x plus 2 dx. Okay, so let's split that up into the three separate integrals that we get, and we're going to pull the coefficients in front. So -1/2 integral of dx over x plus 1 minus 1/2 integral of dx over x plus 1 squared plus 3/2 integral of dx over x plus 2. Okay, so the first and the last ones, clearly that's going to give us something logarithmic, right? So we're going to get a natural log of whatever's inside, of the denominator. So log ln of x plus 1, ln of x plus 2, absolute value bars. This one, though, is just an application of the power rule. So you actually have integral of x to the -2 dx, which is going to give us, if you add 1, x to the -1 over -1. So -1 over x is really the plus c, right? But the plus c will add at the very end, so that doesn't matter. So we end up with -1/2 natural log of x plus 1 absolute value bars. And I'm going to write the logs together. Well, actually, it doesn't matter. -1/2 times -1, so plus 1/2, times 1 over x plus 1 plus 3/2 ln of x plus 2 absolute value bars plus c. And if I clean this up just the tiniest bit, I actually end up with -1/2 ln of x plus 1 plus 3/2 ln of x plus 2 absolute value bars plus 1 over 2x plus 1 plus c. And that's our answer. As you can see, the hardest part, or really the most laborious part of this whole set of skills, is using the linear algebra techniques properly. Okay, so this is a technique that works every time. It's time and work intensive, but it works for any combination of, so if you end up with like 6 variables and 6 equations, this will work, and you don't have to get lost in all the details. Okay. All right, let's see another example, just to to finish, round off the ideas here. And in this next example, I think it should be a little bit easier, but basically we're just going to need to factor first. So we're going to evaluate the integral of 3x plus 5 all over 1 minus 4x plus 4x squared. So notice that 1 minus 4x plus 4x squared, and if you don't have an eye for this, you're going to need to practice a little bit. This is 1 minus 2x squared. So this one's not so bad because we just end up splitting it in two. So we need to find 2 letters now. So the undetermined coefficients a and b. such that that whole right side, the 3x plus 5, so the original rational function that we're integrating can be written as a over 1 minus 2x plus b over 1 minus 2x squared. Okay. So here, let's just go ahead and multiply this out, right? So we get 3x plus 5 equals a times 1 minus 2x plus b. Because when we multiply it by the least common denominator, it'll just be 1 minus 2x. That won't be an issue. So once we do that, then we're done with this problem, really. I mean, there's not too much to say here. We're going to simplify the right side here a little bit. And the same idea applies here, that we're going to, when we split it up into two equations based on, the coefficients for x and the coefficients for the constant terms, we end up with 3 equals negative 2a and 5 equals a plus b. And this immediately lends itself to the solution. A equals negative 3 halves, because if you just divide that first equation by negative 2, you get this. And then plug that into the second equation. So 5 equals negative 3 halves plus b. So 5 plus 3 halves is b. And that means b is 13 over 2. Okay. Then our integral becomes, instead of this whole nastiness, we get negative 3 halves integral of dx over 1 minus 2x plus 13 halves integral of dx over 1 minus 2x squared. Okay, here we're going to be a little bit more careful. We need to perform a correct substitution. So if we let u equal 1 minus 2x, right, then du is going to be negative 2 dx. So replacing dx means we're going to have to multiply by negative 1 half. So we end up with negative 3 halves times negative 1 half. The integral of du over u. And same thing with the other side, right? So if we do the exact same substitution, then we end up with, and just for the sake of, we end up with different integrals, so it doesn't matter, but I'll use a different variable. V equals 1 minus 2x, which means dv equals negative 2 dx. It means the second integral, we're going to pull out a negative 1 half again, times the integral of du over u squared. And that actually is not going to be too bad, because when we integrate that, it'll be that same power rule technique. So putting it all together, this becomes 3/4 natural log of absolute value of 1 minus 2x minus 13/4, or plus as well, because then there's another negative that comes out, plus 13/4 times 1 over 1 minus 2x plus c. And that's our integral, or antiderivative, I should say. Okay, in the next video, we're going to introduce the next case, case 3, irreducible